So welcome everyone to the SNAPP seminar series. So today we are very happy to have Jose Blanchet joining us. So Jose probably needs no introduction for this audience, so I'll keep the introduction brief. Jose is a professor of MS&E at Stanford, and prior to joining MS&E, he was a professor at Columbia, and then prior to that, he taught at Harvard. Jose is a recipient of the 2010 Erlang Prize and then several best publication awards in areas such as applied probability, simulation, and operations management. He also received a PECASE Award. He has research interests in applied probability, distributionally robust optimization, machine learning, and the Monte Carlo methods. And today he's going to talk about optimal transport-based distributionally robust optimization. Jose, please.
Thank you, Johan, and thanks very much to the organizers for the for inviting me, and thanks for the nice introduction. Thanks for your patience because I was slow in sending the material, and the reason is because I was trying to think exactly what would be a good thing to have for the audience. So the way in which I have thought about this talk is a bit of a kind of I'm not going to say tutorial because I'm not going to spend a lot of time kind of talking about the details, but it's kind of like a roadmap or like a user guide of the things that we have been doing, and also I'm going to talk about the things that need to be done and are potentially interesting problems. But you should feel free to ask any questions at any time. I can just provide more details on some of the topics, and I will not be able to. I don't think I'm going to be able to see the hands. So if there are questions or something, I will rely on somebody, maybe Joan, to tell me if it's possible. So. So this is joint work with a lot of people, and some of them I see here. Nian is one of my former students who just graduated. I just saw him join. I don't know if Karthik is around. Probably not because he's in Singapore. But Viet and the others, I'll explain. So the general goal of this talk is to talk about distributionally robust optimization. So this is an area that it's now not as new to me, but I started working on this around the time I joined Stanford. In fact, around 2007, and I actually entered the area from a very applied probability standpoint. Like I wanted to. The original goal we started with was questions of the sort. Okay, you have data. And we develop a lot in this area, diffusion approximations. That has been one of the themes and one machinery that we have used repeatedly. I also was thinking about rare event estimation. So what happens when I concentrated a lot on kind of developing algorithms, but something that bugged me was the models are very hard to estimate at the level of precision at which we actually test the algorithms, right? So with this idea of, okay, is there a way, how can you give me the data, I create a model, and somehow use the diffusion as a benchmark, but have a sense of like a way to control errors for path-dependent functionals that are, pre-asymptotic, right? Or something that I can estimate just a single quantity. I estimate with the data, and then I try to estimate errors for all sample paths of diffusion approximation. So that was kind of like the beginning of how we approach this problem. And at the time when we were thinking about that around 2016, there was a parallel sort of trend of ideas going on, which we were not aware of at that time, which were developed by Dan Kuhn from EPFL and his group. And over these 4 or 5 years, it has been sort of great to kind of being interacting and sort of like trying to sort of, join this effort, right? And the goal of the talk is to give you a sense of what is the sort of like a panoramic view of an overview of what's going on and what the questions are, etc. And many of these questions that we started with in the group in 2017 that I think touch a lot on interesting topics in applied probability are still kind of on hold, right? I mean, it's it's time to perhaps go back and try to kind of understand things better. So I'm not gonna use the queuing examples. I'm gonna use more like finance examples because and this could be the topic of a whole completely different conversation. But the data in these types of examples, is just easier, at least for how to there are issues that I'm going to talk about, like choosing the elements of the modeling that actually are easier to illustrate with a finance case. But then the goal is to talk about distributional robust optimization via optimal transports. This is something that might be new to some people in the audience, and I'll talk about what is optimal transport and as a tool to quantify and mitigate model error. Some of the talk I've given in some places, some of these might be repetition to some of you. I apologize, but I think there will be something new for everybody. So examples, right, of places where you can see this model error, virtually in any application in which you use stochastic models and where you kind of commit to a model. And this is actually the way in which we have been operating. Largely in applied probability, you have a model, you have a class of models that we study, and all of these have model error. So that's why it's kind of important to use this. But portfolio choice, right? You take data and then you commit to a portfolio and you deploy it and you see how it's going to do. And of course, the past is different from the future. So accounting for that is kind of important and interesting. And insurance, yeah, this is a topic that has been of great interest to me since several years. In the context of climate change and non-stationarities, that's an issue where model error is important to quantify. And in general, what we are seeing is in machine learning, these techniques based on optimal transport and distributional robust optimization are actually very related to a whole host of regularization tools that are used in machine learning, and we are going to talk about that. So if you take, let me anchor the conversation on a specific example, which is portfolio optimization. Okay, so in portfolio optimization, this the most popular version that you perhaps can think of, you have your allocations, your strategies, that those are denoted in, and that will be denoted throughout the rest of the talk as theta. You have returns that you collect. You build a model, so those are denoted as X. The portfolio is in D dimensions, and mean variance criterion is something like this, right? So you want to minimize the variance. This thing is the variance. I have this alpha here, right? So when you minimize this mean square error, you get the variance of the portfolio. So this is variance under the true distribution of the portfolio, and subject to return constraint, which I am expressing here in a Lagrangian form with this eta parameter. That is, eta is the risk aversion, coefficient of risk aversion. So this is equivalent. This is exactly mean variance portfolio selection, right? And the problem is that this P star is not known. So what the standard strategy is to build a data-driven version, so perhaps fit a model to the returns, or if you want to be fully non-parametric, you just simply use the data, right, from the returns, collected data, and then you look at the empirical version of this problem. Okay. Now the problem here is that the data, of course, is an imperfect reflection of reality, and if you want to recognize that that this is the case, and you want to make sure that you use apply a portfolio selection strategy that captures the notion of, there could be a mistake in the model, and you want to find a strategy that is going to perform well, even if there are mistakes in the model that might hurt you a lot. You can introduce this formulation where you have this role of kind of this max, which you can think of it as a consultant, right? Somebody who is going to explore the impact of your out of sample mistakes, right? Or the impact of model discrepancies relative to your benchmark, your PN, and you want to kind of like have this, endow this player, this consultant or artificial player with attributes. These attributes are going to be described by this optimal transport cost, and you also want to endow this player that in the end is like a helper, right? With power, right? So attributes and a power, which is this delta. So when you combine this choice of attributes and you ask your helper, okay, explore what if something happens with such and such asset in the future, if there is, what would happen if there was a big movement or discrepancy relative to the past, how would that affect me? And the combination of that, exploration, this exploration is done in a very efficient way through the solution of this maximization problem. You make your decision. So that's one way of interpreting this. Not necessarily there is some adversary, but it's an efficient way of actually reacting to what is not known. In the past, when I have given talks like this, I get questions of the sort, why this is a good idea, right? Maybe this is too pessimistic, and there is a decision theoretic foundation for this that is studied by economists like Gilboa and Smethier, and so this sort of makes sense. And there are examples that justify using this. There is a very famous thing called the Ellsberg paradox. Daniel Ellsberg was a psychologist where he created games in which people you don't know, you have an urn and you don't know how many balls are there, and realize that a lot of people make decisions that are consistent with this min-max type formulation. So there is an element of optimality in the sense of decision theoretic sort of foundations of this, but a lot of questions about that are still unknown, and I'll touch on that a little bit. So the questions, right, that you might have at this point is, why is optimal transport? Why optimal transport? And maybe even more fundamental, what is optimal transport anyway? And what's the intuition? How do you choose delta? Are there any statistical guarantees? How to choose this transportation cost? And this is a very, very fundamental question that I think is still not fully understood. And this is one of the reasons, like, if we fully understood what was the decision sort of theoretic underpinnings of this approach, then we would understand better how to choose this cost function from that standpoint, and we don't. So that's also open. From a more pragmatic standpoint, you say, well, yes, this sort of makes sense, but come on, is this tractable, right? I mean, you're trying to find this game, right? And is this tractable? Is there a value of the game, right? These things, do they swap? Is there a Nash equilibrium? And questions beyond that, right? What about, decision rules that are, fully non-parametric, not just affine? What about constraints, Martingale constraints, and so on and so forth, right? Why, adding constraints to your adversary, etc. Okay. So these are questions that I hope to discuss. So while I'll encourage you to keep this portfolio optimization problem in mind, many of the results, except for tractability, the tractability results really require the affine decision rules. But most of what I'm going to discuss transfers to this problem. Okay, so the more general problem where you have a loss that is convex in theta, and you have the randomness, right? So this is general loss. So why optimal transport? Well, I mean, if you think about the ways in which you can model changing the distribution or changing a model, there are basically two ways, right, of in which you can model things. One way is you change the likelihood of the outcome. So your perceived likelihood is one, but the true likelihood, or the likelihood you are going to face out of sample, is a different one. So changing likelihood is one approach, right? Change the likelihood or perturb the likelihood. Another approach is a contamination approach, is you perturb the outcome. So you think the outcome was such and such, the returns, but the real outcome was something different. So you add a perturbation, right? So these are the two ways. I don't think there is any other, okay, approach. Of course, you can add, you know, moment problems, but that is just going to be more and more pessimistic, and you also want to constrain the upper bounds, or don't endow the adversary with a lot of more power, because you're going to end up with very conservative solutions. So you can add constraints, but fundamentally these are the only two ways. And this approach, the first one, based on likelihood, leads to distributionally robust optimization based on divergence, and has been very, very popular in economics, particularly this book by Hansen and Sargent, 2008, that, you know, made this approach very, very popular. But the approach actually can be traced back to the 1999, 2000s in the control community. It's related to H infinity controls, and is, you know, is one that has also been studied in operations research, right, in finance, and more recently in machine learning. Okay. The Wasserstein approach, in fact, is related to moment constraints. So this paper of Scarf is the earliest paper I know that uses moment constraints, and moment constraints are linear constraints, and the math is similar, although it's not exactly Wasserstein. There are these papers by Huber and Hampel, you know, early, that actually use exactly the Wasserstein distance. The Wasserstein distance is a particular case of optimal transport. This work, you know, has been also used in finance and in stochastic optimization, but, you know, mostly the examples in one dimension. And then there are, you know, more recent papers on stochastic optimization, exploring the connections to regularization. And this is, you know, this work that I was telling by Dan and his group. There are many, many other papers. And then this, you know, the work that we produce with the idea of, you know, doing, you know, applying to stochastic processes and things that are more directly related to APS. And then work related to more machine learning and adversarial training. Okay, so this you can see that this is more recent, and these things are treated separately as if you either have one or the other, right? But you know, if you take a more general view of optimal transport and not just Wasserstein distance, it turns out that you can fold both of these things in just optimal transport. So both approach A and approach B is just the same. It's just part of optimal transport. Okay. So what is optimal transport anyway, right? So if you give me two distributions, P and P0, you give me a ground transportation cost. So this is the cost of transferring a unit of mass from location Y to location X, right? And you solve the linear programming problem, which represents what's the minimum cost of moving a pile, right, of dirt into some other shape or thing, right? In this case, it's represented by a castle. This is your mu, and this is P, and this is P0. You solve, you know, you compute what's the cheapest way, and this solution of this problem is a linear programming problem. This is the optimal transport cost. Okay, and this is an infinite dimensional linear program. It holds in great generality. The space, you know, this P and P0, these outcomes can take values in a Pauli space. So it's great for things like, you know, you want to compare a random walk versus a diffusion and look how far they are. or a diffusion approximation, etc. This can accommodate these types of comparisons. Okay, and there is a very rich duality theory, which you can find in the book of Cedric Villani. This is the nicest infinite dimensional linear program you can think of. The strong duality holds on the very mild assumptions. The C cost function here, all what it has to do, it has to be non-negative and lower semi-continuous. Could be infinity in some points. That's perfectly fine. And in fact, it's very, very helpful to actually have the infinity, as I will show you. So what is optimal transport distributionally robust optimization? Well, it's something, it's very natural. It's another linear programming problem. What it does is this thing is the expectation under the measure P of the loss, right? So when you marginalize X's, you just get Y. And this thing is just simply saying that there exists a pi such that the optimal the transport cost is less than delta. This is the same as saying the minimum, right? Minimum over pi, expected value of pi under pi of cxy less or equal to delta. And this constraint here simply says that the marginal over x has to be your model. And because you are choosing over all pi's and you're maximizing this objective function, you can just simply drop this. So this is equivalent to saying, you need to find a pi, a coupling that maximizes the loss, right, for the marginal y. You anchor the marginal of x at p0, and you just need to find, the worst case pi that satisfies that the distance is less than delta, right? So you can put the mean or drop it. Is equivalent problem in this case because it appears in the constraints. So if you kind of replace this by summations, so this is a summation over y, summation over x, the discrete, it's very easy to guess what the dual problem is. In fact, this problem is almost in a standard form, and the dual is going to take this form. Okay, this was worked out at the level of generality, at the same level of generality of optimal transport was posted in the archive in 2016. There are other papers that follow slightly later, similar results. But you can get the almost the same level of generality. The only difference is that the maximum might not be achieved, whereas in the optimal transport case, it is achieved. But in terms of assumptions, it's the same assumptions. Lower semi-continuous, you can put infinities, etc. And this is important. So because when you select a cost function that is a metric, to some power, you get something that is called the R type Wasserstein distance. And if you do something like this, right? If you lift, if you want to introduce divergence or pullback library, and you want to see that as a particular case of optimal transport, you need to lift the outcome of the stochastic process. You need to add the likelihood ratio and consider the likelihood ratio itself as a random element. So once you do that lift at the beginning, the likelihood ratio is just 1 because your baseline model is just P0. But if you introduce this transport cost, right, you have a phi. Could be the phi, the case of phi of x equal to x log x is the pullback library case. This one. You just put it here. You simply say don't move the points, just concentrate on the outcomes, make sure that you don't send anything, no negative weight. And you just simply send the weights according to this cost function. You need to add also a constraint, but this constraint is very easy to deal with. And you recover the phi divergence as a particular case, okay? With this additional constraint. So no problem, right? So this answers the question, right? So intuitively, optimal transport allows you to move points and allows you to reweight, allows you to do both, and this is the most general way in which you can perturb things. Some other nice things about optimal transport that we have discovered in the last years is that, well, phi divergence turns out is known as variance regularization. So you can if you want to regularize with respect to the variance in some learning problems that you can obtain as asymptotically with phi divergence. If you want to regularize with the norm of for example, your policy, right? The norm of the loss, you can obtain that with direct optimal transport using Wasserstein distance, right? So these are examples. In this case, this recovers the square root lasso. You can apply to portfolio selection, you get this norm. And this is when you have these cost functions that are of the form of norm, right? So this is Wasserstein distance. Okay, and this is the typical way in which it's used. Now, so I will come back to this later, but basically this shows shrinkage properties. So now the next question that you might have is, okay, how do you choose the size of uncertainty? And there are, okay, so let me make an observation. So this is something called square root lasso. It's exactly, this is not approximate, the square root lasso, okay? And the high dimensional statistics community has studied a lot the problem of how to choose the regularization parameter. Regularization parameter corresponds to the size of uncertainty. And so we have a way for the very specific cases of these types of loss functions to see whether whether the game formulation, this one, can lead to a criterion that is comparable, okay, to what the statisticians have done. So here is one criteria that is inspired and that is informed by the game. The criterion that is informed by the game is you take the point of view that you look at all the decisions that are inside the ball, and you believe that these decisions are all the plausible decisions that could happen when you realize and when you deploy. Okay, outside of the sample, these are plausible, assuming that you have selected this adversary in a reasonable way. And so one very natural idea is to minimize the set of all plausible decisions subject to the constraint that you cover the correct decision, the one that would have been, if you knew what the model was, the one that you're going to see in the future. So this optimization problem, we think, well, it's informed by the game, it's informed by the cost function, and it's very natural. You're minimizing, the amount of uncertainty. And it turns out that this optimization problem is equivalent to a projection problem. So the optimization problem says, you want to find the smallest delta. So let's look at the constraint. The constraint says that the true decision has to appear in this set lambda, and this lambda you can interpret as the projection of this uncertainty set in the probabilities in the decision space. So these are all the models that make theta star correct. Okay. And correctness in the case of convex losses means first order optimality condition. So you have a model inside the ball of size delta that makes theta star correct, even if and only if the distance from the center of the ball to the space of models that makes theta star correct is less than delta. And so this is why this constraint is the same as this projection problem. So you look at the projection, and you want the projection to be less than delta. So the solution to the optimization problem is just find the quantile of this thing, of the projection. So this leads to several papers that we wrote about how to. This one is the latest on how to compute these projections and projections in infinite dimensions. And using these projections for hypothesis testing, for fairness. I didn't add that reference here, but this tutorial, this management science and engineering tutorial that was presented at Informs last year, discusses these applications to fairness. So this idea of projecting is used also in the context of hypothesis testing and other applications. But now, the question is, okay, so you have this projection, nice. Turns out that this projection is also a linear programming problem. And you can ask, what is the asymptotic statistic under the null hypothesis that Pn, converges to P star. And it turns out that you can compute that. You can obtain what's that asymptotic statistic. And that asymptotic statistic is the Fenchel transform of some convex function evaluated as a Gaussian. This is a Gaussian vector, okay? And I don't want to give the details, but this in the particular case when the cost function is of quadratic form and just being a high square distribution. And again, I encourage you to go and read this tutorial. This tutorial explains how to, what are the shapes of these convex functions. But now the idea is that you can now select the 95% quantile of this distribution and divide by the number of samples and use that as the choice of delta. This in particular avoids cross-validation. And it works very well in practice, surprisingly. So here is one example of in the context of finance, right? So when we do it for portfolio optimization, what was very surprising to me is that this thing did so well. And I'm gonna, we compare this. This is a paper that appeared early this year in management science. And I have the reference earlier. This is the portfolio optimization paper. We were asked by the referees to do this many times, and I'm so grateful we were pushed to do that. So what we did is we selected 5 out of the S&P 500s. We keep sampling with replacement 100 different samples of portfolios. We retrain, so we have a data set that goes from 1998 to 2018, I think, or 2017. And so we trained first from 1990 to 2000. We find the policy. We compute the delta using this distribution, and then we do apply rolling horizon, recomputing delta every month, right? 2000 monthly data, monthly rolling horizon. This is what we did. We compared to things like, Black Litterman, a model of Garud, and others, just a standard single period, equal weighted. And we also did compare against the stochastic control, which worked really bad because, you need to kind of have a model that didn't work well. So I'm not showing that. And the thing that was the most competitive, and this is very well known in finance, actually, just equally weighted portfolios tend to be very competitive. So we see we beat the equally weighted portfolio. So after these 100 samples, we average. This is the average of all of the results of performance, and we beat them just by a tiny bit. Okay, we do similar to French FAMA. I think this is the 3 or 5 factor model French FAMA, but the French FAMA model uses more information. This is important to keep in mind. It uses the additional factors information, whereas this is just purely data driven. Now, when it comes to actually comparing to so the blue is this method. The secret sauce is the delta. This is exactly the point. That's why I'm showing this. And then the equally weighted is the orange one. It's small, but when you actually invest, this thing could be significant. When you actually compare the Sharpe ratio between the blue and the orange one, it looks like this. Okay, so the blue is or Sharpe ratio, is the DRO Sharpe ratio, and this is the orange is the equally weighted. You can see that you can reject that, but this is not the same. Okay, so it performs, it corrects the Sharpe ratio, and but it works as comparable to this French FAMA without additional information. So surprising. This is, we thought it was too good to be true. So about the question of how do you can choose transportation costs and how do you can use additional information. Here is one way in which we have done that. This is still largely open, but one way where you can do this in a meaningful way is the following. So you can, instead of using just the past data, you can combine the past data with market information. Here is one way to do that. So you can use the implied volatility as a proxy for what the market thinks is going to happen in the future. And so the intuition is the following. So if the market thinks that there will be an asset that that is very volatile, something is going on, then the volatility is going to be high, right? The implied volatility. So we look at an implied volatility index. And if the implied volatility is high, then we choose a cost that is inversely proportional to the implied volatility. So then the cost of transporting, like when I use my adversary and I say explore what if outside of the sample, the adversary is going to be cheap for the adversary to explore that particular asset that has high implied volatility. And that is going to be, the mathematical program is just going to just reflect that in the overall decision. So here, in this case, this AI depends on the xi prime. So this is not of Wasserstein type. This is more of the form you transport x, y. This is the transportation final end, right? This is the beginning. And this is kind of more like of the form y minus x transpose. The A depends on the data. And then you have 1 minus O. So this is like a local, we call it local Mahalanobis cost. We did this thing, and here is something also that we found was super interesting. This is the efficient frontier. This is supposed to be efficient frontier. So we all know, we have learned in our courses in finance that it looks like that. This is the risk, and this is return. And this is when you do data, simulated data, it looks exactly like this. As you increase the uncertainty set, of course, the decisions become not in the efficient frontier, right? Now they are not efficient because you are kind of like playing against something and you are testing it in a simulated reality, okay? But when you go outside this, this is actually the non-DRO. So it's completely different. We didn't actually do this experiment in the management science paper. This was in the math of war paper. Like, these shapes here, improve. So this is, I still do not know how to explain this thing that you actually the shape gets inverted when you go outside of the sample. And we didn't do as many experiments, but this is what we saw happens. You can take a look at this paper. There was a talk. It was a question, I think.
Yeah, I think Venkat has a question.
Yes.
I thought a few slides back, how about, I think, the plot of the method against, SP 500 and others. How does this compare to SPDR?
I don't know. I don't know. I did this time. I don't know. I haven't done the comparison. Okay. And in fact, I'm sorry, but I don't. What is SPDR?
Venkat.
I just unmuted myself. Yeah, Jose. Yeah, SPDR is the ETF that tracks it's called spiders. If you want to invest in the S&P.
Yeah, got it, right.
So I mean, people are anyway providing something that tracks the S&P. So I was wondering how you compare to that.
Yeah, this is very. I suppose if you are tracking the S&P, this is the S&P here. Is this one?
That's right.
So.
Oh, I see. Oh, I mean, that's the S&P. Oh, I see. Okay.
That's the S&P. Yes.
Oh, sorry.
So it would be some. No
I
problem.
thought the S&P was right up there with your graph, so I was confused. Thank you.
Yeah, no, it's sorry, my mistake. Actually, Lisa Goldberg, when I presented that, she had the same. I should have changed the color. Sorry about that.
Okay, thank you. Yeah.
Yes. So Lisa was very interesting. As I said, like we were really kind of asked a lot about this. In the paper we have lots of histograms and yeah. Thanks, Venkat. So now, in terms of like tractability, okay, so turns out for affine decision rules, this stuff is tractable as long as this delta naught is not very large, as long as the adversary is not very large. And intuitively, what's going on is that if you look at this kind of general, for example, cost functions, or you could be a cost function also works for the form. You have some cost function that is really of this form for C convex, okay? So something that you can do is you can split the inner optimization and basically reduce the problem to a one-dimensional optimization problem. So it's a little bit of algebra is massaging this thing, but you know, what is important here, I think I'm going to emphasize is two things. The algebra of kind of going from, you know, reducing to one dimension typically involves, you know, expressing this as in the terms of a Fenchel, Fenchel dual, and kind of like, you know, holding the affine decision rule to a particular value of z, and, you know, just optimizing over z. So you're reducing it to one dimension. So the algebra is pretty direct and you know, very standard. But what is important is over the course of the algebra, if you really want the problem to be tractable, to enjoy the, you know, like a preconditioning factor, you really need to think a little bit about what's the Lagrange multiplier, how to scale it, and what's the shape of the adversary. So once you introduce those scalings, turns out that after that rescaling, the problem actually becomes nice, strongly convex, uniformly in a neighborhood of the delta, right? The uncertainty set and so on. But most importantly, it gives you an insight of what the adversary is doing, right? So the adversary is kind of moving things an amount that is of order square root of delta for cost functions that are of this form, cost functions that are like this. Okay. And so the inner optimization, now the thing is one dimensional, but it's still the difference of two convex functions. So it's a little bit tricky, but you know, in the paper, for these particular cost functions, at least we are able to say, okay, you know, this z can actually be compactified, and you can find the root of these problems efficiently. So for these problems, right, you know, if they are affine decision rules, and your theta and your delta is not too big, but fixed, right, then these problems are tractable. And whether these problems are tractable in full generality, well, in some cases, I'll explain. You can reduce it to a problem that you can plug in software, and Dan Kuhn has papers around that, and I'll provide the references. But beyond that, I think is not as obvious. So you can get, you know, a stochastic gradient descent where you pay this log 1/epsilon price because you need to search for this z, but it's essentially as you didn't have the adversary. Okay, so in practice, really looks the same. No kind of degradation in convexity and in complexity. So this is the paper I was. This is a tutorial of Dan. And it discusses cases where, you know, when L is the maximum of affine functions, you can have a dual reformulation, you can plug in software, and those are this is the only types, you know, cases, you know, very special cases where you can actually get stuff that could be tractable for, you know, more general than just affine decisions. So the loss function is affine, not the decisions are affine. So about the value of the game, well, you know, I'm going to talk about. I think I have 15 minutes left. So you know, there are. This is a result that actually was produced in a paper. The goal of the paper was really statistics and confidence intervals. But what we realized, remember earlier in the talk, I told you about this set lambda delta Pn, which is kind of the set, the plausible set. Right, so the set of plausible decisions, and actually to prove that the DRO solution is inside this set itself, you know, the theta DRO, because of the definition in which we say, well, there exists a model that is inside the ball, and for that model, the theta star is optimal. If you think a little bit about it, you are first kind of like you are kind of fixing the theta star and then doing, you know, picking the models. So you're kind of doing something like this when you actually test whether this is in the ball or not. And we needed to kind of like check whether this swaps. So basically the reason for actually this was very practical, was really, you know, when you think of these sets, these kind of natural sets that arrive from the formulation, like confidence sets. Well, is the decision you are making inside the confidence set, because otherwise it wouldn't make any sense. And for that, we actually needed this swap. And this swap doesn't follow directly from Sion's theorem. And you might think, well, yes, I mean, you have convexity here, P, what nicer concave function you can ask for something that is linear in P. But actually the thing that fails is the natural topology to endow the functional as a function of P is the weak topology. And these things like this maximization, this stuff is compact in the weak topology typically, but the function is not upper semi-continuous because that involves uniform integrability that you don't have. So that's a tricky thing, but you have it in substantial generality. And instead of actually telling you about how to do that, I'm going to take this as an excuse, this min max, right? So it turns out that yes, you actually have it here, and you have the DRO solution with the empirical risk minimization solution, and with 95% confidence the theta star solution. Okay, but as an excuse for this swap of min max problem, I'm going to tell you about something that I think is super cool. And this is a little bit kind of a digression, but I want to show you this. So I'm going to show you why this min max works. How can you see it at least in a very cool setting. And this is the setting of a Bayesian non-parametric regression. So this will illustrate policies that are fully non-parametric. So you want to imagine that you want to compute. You want to learn this function yxi. You have points in some domain, and then you measure those. This is yx with an error, right? This is error. Another problem, this also motivated by uncertainty quantification is you really want to learn a physics law, like for example a linear physics law, and you observe data, right, x1, etc., m with noise, right, and you want to learn the u. Okay, you might also observe the b, right, values of b, and you want to learn the u as well, or observe u and want to learn a b, like an inverse problem. Okay, so this is the motivation, problems like this, and the non-parametric Bayesian non-parametric approach would be, okay, impose a Gaussian prior on this b. You can think of T identity if you want, that's okay. Impose a Gaussian prior on B and on the errors, and one such prior could be, for example, this one. So this is, imagine that the domain D is the interval 0, 1. This is a Brownian bridge when alpha is equal to 1. Okay, so you have this prior, and then you want to find the best predictor of the U given the observations, the Y's. When delta is equal to 0 here, of course, this becomes just Gaussian, and we know that this is phi is in L2, right? So phi is in L2. So we know this would be just the conditional expectation, and we know that's an affine function of the Y's. Okay, but in this case, this is a game where the state space, the outcomes, are in this infinite dimensional space of functions. The decision is fully non-parametric, right? And this would be the DRO problem. Now, to give you intuition, this alpha here, you can think of this alpha as the controlling the amount of smoothness of the adversary. So if alpha is equal to 1, the amount of smoothness is this parameter minus d divided by 2. So when d is equal to 1, that's a half. So alpha minus 1/2 is equal to 1/2. And Brownian motion indeed is basically Hilbert. Hilbert continues with parameter a half. So this is what I mean, right, by the amount of smoothness is the Hilbert parameter. Or how many derivatives do you have, and then the remaining is just the Hilbert parameter of the last derivative, right? So Brownian motion is not differentiable; it's just Hilbert. So so now I'm going to explain to you what is this cost function that we use for this problem. The cost function is, is a norm on a space that controls the smoothness, right? These are called Sobolev spaces, and you can think of these ENs. This is like EN. Okay, the EN in general can be, for example, the eigenvectors of the Laplacian on some domain. These are, in fact, one in the interval 0, 1, right? The eigenvectors, the cosines as well. So you have these smooth functions, and you can think of, that this parameter beta control the smoothness. This beta is smooth, beta minus d half smooth. So we impose the norm in this space, and this is the norm we endow the adversary with. So in other words, the adversarial paths can be anything. Give me, this is the prior, right? Or in d dimensions, something that is based on the eigenvectors of the Laplacian. And then the adversary can choose anything that could be even more rough or less smooth than the prior. Okay, so if beta is less than alpha, then I have adversaries that are more rougher than the prior. So these types of problems, like arise in, for example, Kalman filter, or this has been studied by the signal processing community in the past, not at the level of generality I'm considering, but for multidimensional versions of the problem with the Wasserstein, with the divergence, phi divergence as balls. And one thing that happens is if you try to do a phi divergence approach here, it would be impossible for you to have adversaries that are rougher, that induce potential paths that are less smooth. That cannot happen with phi divergence because the degree of smoothness is something that has to be preserved because that's a 0-1 type set. So the result is this result that is kind of surprising. I think is kind of cool. So I mean, basically says like, look, if your space, your transformation is bounded, right? If you basically, when T is identity, this is nothing. This always holds, right? But if you go from something that is like, you want to solve a PDE, you want to have rough, you make your adversary rougher, well, you need to have at least second derivative. This is basically what it says. But you can choose beta less than your prior. Then min max equal to max min. But the cool thing is that the worst case adversary is also Gaussian, and therefore the best predictor is also affine. In other words, you can have like, if you start with a model that is non-parametric, Bayesian non-parametric that is Gaussian, and you robustify, inside these balls there are all sorts of models, not only Gaussians, basically full generality. The worst case response is also Gaussian, and so that's actually tells you that Gaussian models could be robust. Not every Gaussian model is right, but within the family of Gaussian models in this very general non-parametric setting, you have something that is robust. We use then results from semi-definite programming by Dan and his group to compute, to find approximations for these worst case adversaries by discretizing. The discretization is also stable. So in the last 5 minutes, I just want to walk you through why this works, because actually the technology, or like the basic sort of like inner workings of the proofs are very easy to understand. So for an upper bound, you start with this. This is the original DRO problem. You relax, so you say, well, I'm going to consider just affine functions, right? Then, given that the function is affine, you apply this duality result. And in the duality result, you see that this optimization problem is quadratic. This is just quadratic program. And so the optimal solution to this quadratic problem ends up being an affine function of the data, right? Phi was affine, right? Has been set affine. And so this is ends up being just affine because the derivative of a quadratic is linear. So the optimal decision is affine, and you have an optimal sort of also decision for the upper bound for the player. So now you have a kind of like a choice, right? A candidate for the solution of this problem. When you go to the lower bound, you start, you have this candidate in mind, which is already Gaussian because everything was affine, and an affine function of the data, which is P0. There should be P0 here. And then what we do is we apply, so this is weak duality. And then here we just simply plug in, here is plugin, your guess from here. And then now it's just the rest is computation, right? So, very simple. Well, there is a lot of work in actually just carrying this through, but this is basically why it preserves the Gaussian property, because this is quadratic, right? And this is important in the definition of the adversary, right? So these are just a few pictures. This is the, this is a case where you have 1.5 derivatives, and this is something that is even rougher than Brownian motion. So there is almost, so it's 0.1 Helder, right? Like some fractional Brownian bridge with very short-term correlations. And you can see, so one difference between the Kullback-Leibler case. In the Kullback-Leibler case, you don't get actually different policies. You just get an expanded policy, but not the shape. The shape you cannot get different shapes for the worst case adversary. Whereas here, you get different shapes, and you can see this. These are cases where the observed points are here, and you can see that the worst case adversary tries to go outside in the places where you don't have observation. So this is based on 500 paths. Okay, so the paper has like also the shape of the covariance function, etc. I wanted to talk about Martingale constraints, but I think I'm not going to have time. So, but it's posted, and I'll be happy to talk. This is going to be presented at the Informs meeting. So if you're going to go there, it's going to be presented by my postdoc Jiajin, and you can go. And this is just serve as advertising for her talk. There will be also I will also give a talk about Martingale constraints in the context of dynamic optimization problems. But all of this that I presented is static. So the conclusions is optimal transport is versatile, powerful, insightful, I hope. You can use side information to enrich the model formulation. Is often tractable, but needs more work here if you want to go beyond affine decision roles and larger uncertainty sets. And you can add Martingale constraints and deal with non-parametric robustness. So this is a very rich area, very in flux, very active. I'm just going to leave it at that.
Well, let's thank Jose for a very nice overview of this area and of some of these works here. I think we have time for 1 or 2 questions.
I would like to hear a little bit about Martingale constraints, if possible. What have you been able to do in that area?
Yes, so we have 2 papers in that area. Well, coming up, so there is one. There is another one with between Peter Glynn, Shengxing Zhu, and myself, where our motivations are problems in finance. And then there is another one that is coming up in the context of linear quadratic control problems, that I'm going to present at Informs. This particular one that I wanted to highlight here, because I was concentrating on the setting of sort of static optimization and regularization. What it shows is that if you add Martingale constraints, so look at this form. This is the formulation I presented earlier in the talk that gives rise to something that is like a square root lasso here, right? If you add Martingale constraints, then you obtain something that is that interpolates between a square root lasso and Tikhonov regularization. So when you add Martingale constraints like epsilon equal to 0, you recover exactly Tikhonov regularization. If you put epsilon equal to infinity, you recover a square root lasso type regularization. And this paper sort of like has everything in the middle. So this, when epsilon is equal to infinity, you ignore it. Epsilon equal to 0 is exact Martingale constraint. And you can have regularizations that are sort of like everything in the middle. And we explore like in practice, what does that mean? And it actually ends up being, working very well for some problems, not for everything. But basically the philosophy is that, why do you add constraints? Because you want to constrain the adversary. The adversary sometimes can be very pessimistic. And so having the ability to add these constraints in a way that are tractable is the motivation. So this is what I have for this talk, but there are, you can email me, I can send you the papers. For the other thing in finance, for example, we concentrate on, okay, if you want to solve this complexity problems, the people from finance, Jan Oblodge and many others have been working on these problems, and we look at what the sample complexity to approximate them by, Monte Carlo. We realize that the exact formulation they have is difficult, so we find a different formulation that preserves the Martingale constraints, but add balls, right, Basel-Stein balls that have complexities that are like 1 over square root of n for one-dimensional Martingales, regardless of the time, right? There is a coefficient that depends on time, but basically trying to understand where you can approximate these problems. How do you change them a little bit, like find different variations that actually make them tractable from a sample complexity standpoint? I can send you that.
Well, it certainly sounds very interesting. Thank you very much.
My pleasure.
All right, I guess in the interest of time, let's thank the speaker again for excellent talk. Thank you, Jose.
Thank you, John. Thank you.